Welcome to AI101 series, a no-nonsense guide to artificial intelligence. You can read about me, my books, blogs, and everything in between on my website, rnanda.com. Feel free to reach out to me. My email is on my website. In this part of the series, we will focus on how do machines learn and how do the models get developed. More of what I call as MDLC, Model Development Lifecycle. Again, as a reminder, this is not a hands-on technical coding course. This is meant for more for understanding the concepts and the terminology behind artificial intelligence. In the previous lecture on this series, we talked about deep learning, which is the foundation of artificial intelligence. So neural networks make deep learning successful or make it happen. And neural networks are designed so that they mimic human learning or human brain. That's why you would hear the terms used often that mimic the human brain terms like neurons, synapses, and all that. So any neural network will consist of three layers. The input layer, which receives all raw input, similar to our five senses. The hidden layer is where all the processing happens. And this hidden layer actually consists of multiple layers. It's not just one layer. It should be called hidden layer bucket or whatever other, if we will have to figure out a new term. But essentially it's multiple layers. Some layers would be programmed as you are developing the deep learning algorithm, and some layers will be created by the model itself as it is learning from the data that it ingests. And then the output layer will always have the one output or one neuron. That is the cumulative result of all the entire hidden layer processing. So think about neuron as a small sphere of knowledge. For folks who are used to the traditional programming style, think of neuron as a standalone, fully encapsulated function. So let's say you have a function that does just one thing. Let's say a mathematical function, which will do all processing of addition, subtraction, different mathematical functions, but it only does that. And it is fully standalone, encapsulated, has no dependency on any other function. That is equivalent to a neuron. It's a simplification of the idea, but the concept explains it well. So let's take an example of you want to build a neural network to identify for fraudulent transaction of a credit card. So the input layer may take neurons that will take input of, let's say, location, the size of the transaction, the store. Location means which city or which country and all that. The point of sale, like was it a particular store, a mall, or where did you buy or purchase something. The item was purchased, and we talked about the amount of the transaction, and so it can take multiple inputs, and then the hidden layer will process each of them separately. Each neuron will process it separately and pass on its result to the next layer or the next neuron, or whichever way you have created that neural network or programmed it, and will then hidden layer will process all the cumulative result and will identify whether the transaction is fraudulent or is valid transaction. So maybe, the first layer is only looking at all the location information and trying to see if the location is within your, workplace, within the, certain diameter or certain radius of your workplace or home or other frequently visited places, whether the transaction amount is within the range that you typically buy from that location. The items that you have bought are typically in the range of what you buy usually at that. So there are multiple things that the program can look at, and then make sure that it is a valid transaction. If there's any anomaly, then there are a separate set of rules. It can be, hey, maybe you're buying a big TV, then it can also look at whether it's a festival season or when was the last time you bought a TV. You may be replacing it, or did you buy a house? So there are multiple things that the rules can look at to decide whether the transaction is valid or invalid. Most of the rules you may program initially, but then when you feed the data into this neural network or deep learning algorithm, it will also look at the data of the past transactions, or typically maybe not just yours, but typically within your demographic, the purchasing history, the purchasing trends and all that, and may take that into account before deciding whether your transaction is valid or not. So that is the foundation of deep learning algorithms. You will hear terms like, decision tree, random forest, nearest K. So these are different names of different algorithms. Each algorithm has a specific purpose. You can use one or many of them together to build your deep learning neural network. In the previous course or lecture, you would have, we touched upon this, that there are core three methods by which we make AI models learn: supervised learning, unsupervised learning, and reinforcement learning. The names are self-descriptive. Supervised learning means that the model will learn under the supervision of human beings. Unsupervised learning is that the model will learn without any supervision. It will learn all by itself. And we'll go a little deeper in the next few slides on what this means. And reinforcement learning is where the model learns from its own output and gives itself a feedback from its output. New classes of or methods of AI learning are developing, which are a combination of these. Like semi-supervised learning is a combination of supervised and unsupervised learning. RLHF, which is pioneered by OpenAI with ChatGPT. Reinforcement learning from human feedback. This is a combination of supervised and unsupervised reinforcement learning. So conceptually, so again, think about these as at a conceptual level. Not. So what's supervised learning? So let's say that we have, we want to classify different photographs, whether they are of animals or locations or whatever. So simplistically, let's say cats and dogs, very frequently used example. And we already know the answer. We know that, okay, we have 50 pictures of cats and 50 pictures of dogs. So human supervision is already there. We already know the output that the machine should be predicting these 50 pictures as cat pictures and these 50 pictures as dog pictures. So we build the model and we run this pipeline and we figure out at the end that how accurate the model is by how many predictions it made correctly. So in this case, most of the, or actually all of the data that you have will be labeled. You will already know what the data is telling you. And the output can be measured based on what the input was. Supervised learning is primarily used in classification models, and people also talk about binary output, or binary models where the answer is yes or no. Is it a cat? Yes or no. Is it a dog? Yes or no. True, false. So essentially, it's a 0 or 1 output. The other use is multi-class classification, where you are, saying, so all these 50 pictures are of cat, or all these 100 pictures are of category animals, and so forth. So depending on what you are building the model for, the key thing is that the data is known, it is labeled, the output is already known and to the humans, and then the model is trained based, with the data to make it as accurate as possible to predict if a new set of data is thrown at the model that it has not seen earlier. So let's say you have the model trained for cats and dogs. Now you are using that model to identify, let's say tigers and giraffes, or cars or motorcycles, or whatever. So the main thing is that once a model is trained, the expectation is that the model will be able to classify or categorize any new set of data with the same accuracy. It is also used in regression models, where we are trying to predict one outcome based on many variables. So, the example I use here is sale price of a house. So you want to understand, what would be the sale price of the house given multiple things. Can be location, carpet area or built area, the lot size, zip code or anything. So you have multiple variables and you are building a model to predict a house price. So the key thing is that the ground truth is known in supervised learning. So even if you are building a model to predict sale price of a house, that if it is in a particular zip code or pin code or whatever different terminology we use worldwide, location, and if the house has more bedrooms and more bathrooms, or the size of the house, they have impact on the sale price of the house. So you already have the hypothesis or the ground truth available to you, and you are training the model based on that, so that later on you can throw another set of data and it will be able to predict or classify with similar accuracy. Now again, similar accuracy, and we'll talk about a couple of things, in a subsequent slide, which from technical side you need to understand how to balance the accuracy with variability. Unsupervised learning, on the other hand, is used when you have humongous amount of data and you are trying to understand the ground truth. So continuing the example in the previous slide, you already know in terms of the sale price of the house is impacted by location, carpet area, or all that stuff. But how do you know it? This is something that people say, hey, I can, looking at the, data, any human being or data scientist can predict that, certain things that will have an impact on the house sale price. But then, there will be many anomalies. So for example, let's say you are even in the poshest of localities, house is not very well kept. It is the same, the size of the house, the same carpet area than a neighboring house, but the neighboring house is sold 2x the value of the other house. So that's an anomaly, right? So how do you identify that? Or, you have a, a gut feeling that these may be impacting the house price, but you're not sure. So supervised learning is primarily used when there's a lot of data and it is impossible for a human being to actually make sense out of it, or you are trying to identify the ground truth. So you are, for example, you're trying to identify, hey, what are the things that will impact the sale price of the house? Is it pure dimensions and this thing, or is it, should we add another variable to it called the upkeep of the house? When was it remodeled, or last, or what were the changes that the new owner or the current owner did on the house? So you want to find similarities in the data points to identify the ground truth. And also it is used for anomaly detection, threat detection. Example we took around the fraud detection, the example we took around the credit card transaction. So when to use supervised versus unsupervised learning? These are guardrails, or guidelines, I would say, not guardrails, guidelines. But you can have your own list of or checklist of the criteria that you want to use. But at a high level, the data, is the data labeled or not labeled? If there is you cannot label the data, or you don't have any data that is labeled priorly by somebody else, or you have difficulty labeling the data, then obviously you will use unsupervised learning. You don't know the ground truth, or you know the ground truth. The example that I gave in terms of the ground truth may be that you already know the what features of a house impact the sale price. If you already know it, you're confident, then yes, you use supervised learning. But if you want to understand what features or factors will impact the sale price of the house, then you use unsupervised learning. The data sets, if the data set is too large or too complex for any one person to identify a trend, that means that it is beyond the comprehension of a human being, then obviously unsupervised learning will help. And then there is also a method called reducing dimensionality. So let me give you an example. So continuing on the same example of the sale price of the house. So let's say that you have 10 different feature set that you think really impact the sale price of the house. You say, well, maybe the color of the house also impacts the, we already talked about the, let's say, the plots or lot size, the number of bathrooms, number of rooms, and so forth. But then you also say, well, maybe the color of the house also impacts. Maybe the direction of the house also impacts. Maybe the is there a backyard or no backyard? So these are different features, dimensionalities of the data. Now it becomes too much that okay, do all of these impact the sale price, or there is a weighted average. That means that some things may impact much more than the other. So when you want to reduce this dimensionality, again, so unsupervised learning can help. So this is what they mean when they say reduce dimensionality. And we'll talk about the low variance and high bias for supervised learning, which is true for actually most kind of the models, but they call it out specifically in supervised learning because of the overfitting and underfitting of the model. So reinforcement learning is a totally different ball game altogether. This is as close to human learning as possible. So the philosophy is very similar to how we learn, and this is how we expect the AI model will learn. Think about if you are taking a test, and based on the score you get a feedback, and now you will either focus on improving the score, or if you're happy with it, not do anything. So you are taking a decision based on the feedback loop, and you know, essentially either improve or stay where you are. Continue to do what you're doing. So similarly, in reinforcement learning for AI models, the model will learn from its own output to improve upon its own behavior. Similar to unsupervised learning, the data is not labeled, and where to use it, again, some thumb rules. One is where you want the AI to outperform an expert. If you think back in unsupervised learning and supervised learning, most of the time, or many times, I would say, not most, but many times, human expert can outperform the model with a limited data set. But when it becomes too big, then the AI models are used. But in this case, you want the AI to outperform an expert. And so you make it learn with humongous amount of data that is not possible for a human being, and the AI will outperform the expert. The other thing is that, where no decision-making model is existing as of right now, or something that you cannot 100% rely on, or you want to improve what already exists. So this is where, you will use RLHF, or actually RL, I would say, but then I extend that to HF, like, reinforcement learning using human feedback. Combine the two and you will improve upon the decision-making model that already exists. Or when the end goal is not fixed. So you want the AI to automatically decide what route to take to a destination when it is powering a self-driving car. You don't want to give it a route, but at runtime, at real time, it will decide what route to take based on the traffic conditions, or other situations like the road closure or anything, and will automatically drive itself. So reinforcement learning is getting a lot of traction, and I think it's going to be one of the most powerful use of developing AI models. So one thing that is important to understand is the trade-off. Now the terms I'm using here, bias and variance, are model bias and model variance. Do not confuse bias with the social bias that gets, that people talk about, that AI is biased. This is applicable when you are developing a new model, or you're training a model, or retraining a model. So this is quote unquote technical term that you will hear the developers use: model bias and model variance. So bias is the error rate, and variance is how much error rate varies with each epoch. Epoch is the run of the model, training run of the model. So simple example, let's say you are building a supervised learning model for cats and dogs, again, just to keep it simple, and you have 50 pictures of cats and 50 pictures of dogs. So you train the model with those 100 pictures, or sorry, not 100, but you will have your training set, which may be less than that. But let's say once you have trained the model, during the first round of training, your model will depict, let's say, correctly 80% of the time. That means 80% of the time it says correctly whether it is a cat or a dog. 20% of the time it does not, it misclassifies. So what that means is that your model has bias of 20%. That means an error rate of 20%, that it is wrong 20% of the time. Now let's say you run the same data set and you done another run on the training, and now your model is depicting, or actually has an error rate of 40%. That means it misclassified 40 out of 100 pictures. So this is now a variance. What that means is that in the first run of the training, your model was correct 80%. In the second run, your model was correct only 60%. Now the third time you run it and suddenly your model is, correct 90%. And then you run it fourth time, now it is correct only 50%. So this is variance. Whenever you are building a model, the key thumb rule to look at is that, or aim for, is that you should have as little variance as possible. High bias is fine, and the reason being is that once you know that there's a consistent error rate, then you can focus on correcting that. If it is high variance, the problem is that you will not know where your model is going wrong. So when you're building the AI model, the model bias and model variance are two current terms that you should be cognizant of. There are many, but I just want to bring this out because the term bias is sometimes confused with social bias, which is in the data, while this bias is in the quality of the model that you're creating. So how do the base models get developed? The MDLC. Let's talk about that. So model development lifecycle, or MDLC as I call it. So it's not sequential the way I'm showing it. It can, a few things will be in parallel and we'll talk about it in the next slide. But I just wanted to depict that what are the things that need to be done when you want to develop a base model or a new model. And in some cases, you want to retrain the, existing model with brand new data set, or brand new data or different kind of use. So on the left hand side, once you identify the problem, you also build your hypothesis. And once you understand that, then you collect the data that will be used for the model to, one, validate the hypothesis and then train on it. Then you clean the data. This is something that where we'll talk about the splitting of the data splits, and all the ETL stuff, extract, transform, and load. So there are a lot of very heavy lifting happens during this time. Depending on the size and the complexity of the model, but simple models should not take that much of effort. And then once the data is ready to be ingested by the for the model, then you get into model development. And then testing. Once the model is tested against the hypothesis, then you actually do the training runs, maybe one or multiple, which end up with the once the model is ready to be used and consumed, then the governance takes over. And in my view, AI governance will become a very, very important I would say function in any given organization that is going to build or use AI across whatever business function they want. And once more and more regulations come in, then this will become much more complex task to be done. So be prepared for it if you are getting into the AI space. So I'm splitting this into two different things because we want to talk about the data pipeline and then we will talk about the AI pipeline. These are terms here that you will hear very often. So the data pipelining is actually the preparation of data to train the model for model ingestion. So as I said that, so let's take an example. You want to build an AI model to predict home prices. So that's a problem statement. And now you are building it for, let's say, North America. So now you have defined the scope of the problem, and you are now going to build based on the hypothesis, or you are going to say, well, I want to understand the ground truth or hypothesis. So then you will create, assemble all the raw data Now, if you are already focused on North America, then obviously you will, get all the data, raw data from North American house sales from previous years, and you will curate it, clean it, and make the data ready for AI model to ingest. So you will hear this term, data ingestion. What that means is that the data is going to be read by the AI model through testing and also training and all that. But this is called data science and data pipelining, data preparation. Some people call it pre-processing, uh, and then there's a separate post-processing from the model output and so forth. But essentially, data pipelining. It's a very iterative process, so don't assume that this is you do it once and you're done. You will have to keep doing it till you get to the point of accuracy and the predictions, whatever you're trying to create the AI model for. Till you get to the metrics of success, you will have to keep redoing it. This is why creating an AI based model is something that is very expensive and takes years, sometimes more 1 or 2 years, or maybe more, to get to the point of it being usable. So we talked about the data pipeline. So this is a collection of all the data, whether it is raw data, structured, unstructured, images, are they labeled, not labeled, other modalities like audio, video. So essentially everything that you need for building that AI or training the AI model. Now, this is where the bias, the social bias, or the bias that typically people talk about comes in. Now, this is not the model bias. This is why I had that slide to describe what model bias is. But this is the data actually contains the bias. So, for example, if you are going to use social media data for sentiment analysis, so you should already know that there's a lot of bias in people, hatred, jealousy, and they demean each other. So social media is a cesspool full of hatred, full of nonsense. So all that bias will come into your AI model. A very critical example, if you remember the previous lecture, where I talk about Microsoft's early experiment with chatbot called Tay, because it used social media content and it started misbehaving like within hours, and had to shut down. So key thing, data can make or break your AI model. This is one of the very strong pillars. And data preparation, creating the data pipelining, can be almost as difficult as developing the AI model. Specifically, if the data is not very good structured or has to be cleaned, it has to be debiased, it has to reform it. So there's a lot of stuff that happens as part of the data pipeline and data preparation that people overlook. And then the problem that happens is that the AI model itself will not be of a very high quality. The other thing in when you're working with the data pipeline, you have to understand is data splits. So all data that you will use for AI development will be split into three sets. One is training set, which is the largest, then the validation set and test set. So think about the validation set being set that is used, which validates the performance of the model during the training. So this would be a separate test that the model has not seen while as part of training. So going back to the example that we had, like say we had 100 pictures of cats and dogs. So you can say, well, I will use 50% of that as part of my training set, and 10 or 20% of that in my validation and the rest as test, or whichever, so we'll talk about the data split in the next slide, that what's the thumb rule that you can use. But essentially you are splitting the data into 3 different sets that will be used for 3 different functions. Now here the key thing you have to remember is that all 3 sets should be representative. What that means is that for training you cannot simply take all 50 dog pictures, or you cannot say that I will use 30 dog pictures and 20 cat pictures, and in validation I will use 30 cat pictures and 20 dog pictures, or things like that. So all the 3 sets will be representative, similar representative. So what that means is that, let's say if you have to divide 100 pictures of cat and dogs into training, validation, and test, and let's say you are deciding a split of 80, 10, 10, you will say my then you proportionate 50 pictures as 80, 10, 10, and for both and cats and dogs, and combine that into as training versus validation and test set. So training set, that is used for training the model. Validation, it will validate with each training run whether the model is improving or performing well. And the test, after all the training runs have been completed, then you test against this. So this is something that the model has not seen at all during the training or validation. Same thing, you have to also define your data splits. Typically, I have seen that the most common used data splits is 60% for training, 20% for validation, and 20% of test. Many times I have also seen 80, 10, 10, but very rarely, and extremely rarely I have seen 17, 15, 15. The key thing that you have to understand is that your testing and your validation test set should be of equal size. That will help you balance both the model variance and also bias. And we already talked about data curation, the testing the model against the hypothesis, and model training and retraining. And this is where in the governance, you will have to think out how frequently or how, what cadence you will have for retraining the model, and what data and all that stuff, because the model will get stale if it does not keep learning with the new information. Similarly, like human beings, if you stop learning after your graduation, you will get dated much, much faster. So that's why we say learning is a lifetime endeavor. So AI pipeline, once you have all the training data and everything set, now you have the data pipeline ready. You ingest it into the AI model, you test it, you train it, and then you set out for governance. As we talked about it earlier, the key decisions you will have to make as part of your model development is start with the problem definition. Second, are you going to train a model? Are you going to create a brand new model? Or are you going to, maybe retrain the model on a different data? So this would be part of your model training decisions. And then what type of AI learning that you will use, supervised, unsupervised, and so forth. Then so these are decisions that you will have to take as part of your AI, the model pipeline or AI pipeline development, where you will need to say, okay, I'm going to use this model architecture, and it can be combinations. It doesn't have to be just one. Or I'm going to have multiple rounds of this model development. In the first round, I'm going to use supervised learning, and then I'm going to improve it with RLHF, or I'm going to train it first on this data and then extend that data to this. So for example, that you want to create a AI model that can identify automobiles cars. So you first create the model using a particular architecture and a method of learning that can depict or identify whether it's a Nissan versus it's a the make of the car, right? Then you can to improve, you can say I'm now going to train it further on extension of that. It can not only identify the make of the car but also model of the car. Then you can say I'm going to extend it to even train whether it's a SUV versus a car versus a truck or whatever. So essentially you can combine multiple, and this is the decision that you will have to take or your team will have to take in terms of what is it that you're going to why are you developing, what problem are you trying to solve, what is your hypothesis for that particular training run and model, and then so you have to go through the data pipelining and the model pipelining tasks when you develop it. So with this, I hope you understood how the model development happens, what is the role that hypothesis and data play. And then we'll talk about maybe in the next lecture in the series on if you are going to use a pre-trained model, you have to be cautious about multiple things. And specifically, if you're going to use a third-party model, you have to make sure that it was not trained on very biased or non-relevant data, especially for business. In consumer market, I think everything goes because it's when it is free, they don't care. The quality they keep improving obviously because they still have to have the users using it, but they're not as critical as a business would be. Consumers are not as critical as a business would be because there you have a lot at stake. If you like it, please follow the channel, share it, like it, comment, and reach out to me. I'll be more than happy to have any discussions. Thank you.